Hello class, my name is Mr. Pacheco, and today we'll be talking about analyzing the strange and mysterious, but ultimately beautiful functions of sine and cosine. Some leading questions for this topic are just why sine and cosine look the way they do, and how do they relate to circles, most importantly the unit circle, or circle of radius 1. Our lecture objectives are to learn about and understand how the unit circle pertains to trigonometric functions. Some of our standards are modeling with mathematics, using tools strategically, and looking for and expressing regularity in repeated reasoning. So we're going to start by looking at a circle with a radius of 1. I'm going to draw a right triangle inside of this circle with an angle theta. Now, we should remember from geometry, let me label these sides. Our hypotenuse is going to be 1 because it's equal to the radius of the circle. And this side length will be y, this side length will be x. We should remember from geometry that sine of an angle theta is equal to the opposite over the hypotenuse. And in this case, our opposite here is y, and our hypotenuse is 1. Therefore, we know that sine theta is just equal to the height of the triangle. Now cosine theta, similarly, is going to equal adjacent over hypotenuse. And in this case, our adjacent side is x, and our hypotenuse is 1. So cosine theta is going to just equal the width of our triangle. Now, this circle and all of the right triangles within it are very special. These two realizations about the value of sine and cosine in the context of a unit circle actually unlock a myriad of possibilities within the two functions. But today we'll just be talking about how they relate to the unit circle. So this is the unit circle. It shows us degree and radian measures of a circle radius 1, as well as their corresponding coordinates on the circumference of the circle. These coordinates are in terms of cosine and sine of that angle, as we just found out above here. And we're going to watch this video.
Oi! Need a trip to freshness? Irish Spring is only a shower away.
So come, smell hello. We're here every morn.
Irish Spring! Smell from a nice smelling place!
So we see in this video the value of sine over the unit circle, and how that value over some period of time is going to look. We can see that the value of sine over the unit circle is going to trace out the sine graph. So, think of cosine as your x value, or horizontal distance, and sine as your y value, or vertical distance. Our ordered pairs will be of the form cos theta, sine theta. So there's a lot of stuff to go over in the unit circle, so we're going to go over it in pieces. Starting with the 4 axis directions, we have 0 degrees or 0 radians at the point 1, 0. Now, we're going to stop thinking of the opposite length as an actual triangle and start think of it more as the vertical distance, because you can't have a triangle with a length of 0. So in this case, sine of 0 is going to be a vertical distance of 0 over the hypotenuse, which is 1, which gives us 0. At pi over 2, we have a vertical distance of 1 over the hypotenuse, 1, which gives us 1. At pi, we have a vertical distance of 0 over hypotenuse 1, which gives us 0. And at 3 pi over 2, we have a vertical distance of -1 over the hypotenuse 1, which will give us -1. Now, for cosine, the horizontal distance is going to take place of the vertical distance. So the horizontal distance at 0 is going to be 1 over the hypotenuse 1. At pi over 2, the horizontal distance is 0 over the hypotenuse 1. At pi, the horizontal distance is -1 over the hypotenuse 1. And at 3 pi over 2, the horizontal distance is 0 over the hypotenuse 1. So notice the pattern we have here with negative and positive values of sine and cosine. These values are kind of intuitive since we can see that they're true, and they actually come specifically from the definition of our unit circle. A unit circle is going to have a radius of 1, and it's going to be centered at the origin. Therefore, it's going to go to 1, 0, 0, 1, -1, 0, and 0, -1. So we are going to have to memorize the entire unit circle, and there will be tricks to doing so. But before we go into the actual values of theta, I'd like to show a more reasonable version of these theta values. Right now they seem like arbitrary radian and degree measurements, right? We just have pi over 6 corresponds to 30 degrees, and that corresponds to that order pair. But I want to show that they're based on nicer values than we can actually see. So we know that a circle is going to have 360 degrees of rotation. And so we want our standardized angle measurements to be based on 30-degree increments. So from 0 to pi over 6, we have 30 degrees. From pi over 6 to pi over 3 is going to be 30 degrees. From pi over 3 to pi over 2, we have 30 degrees, and so on. Skipping over that middle section, I will go back to it. I'll come back to it. So, how does 30 degrees correspond to pi over 6? And how does 45 degrees correspond to pi over 4? And how does 60 degrees correspond to pi over 3? Well, what we actually want to do here is get a common denominator of 12, and we want to measure our angles in a fraction of 12. So we know that 15 degrees is going to be pi over 12, which means that 30 degrees is going to be 2 pi over 12, which gives us our first answer here. So 30 degrees, or pi over 6, is also equal to 2 pi over 12. Simplifying that, we get pi over 6, exactly what we need. So now, jumping from 30 degrees to 45 degrees, all we're going to have to do is add a pi over 12. So 45 degrees is going to be 3 pi over 12. And then going from 45 to 60 degrees, we're going to add another pi over 12 to get 4 pi over 12. Now the jump from pi over 3 to pi over 2 is actually not a 15-degree jump, it's actually a 30-degree jump. So we need to add 2 pi over 2. So adding 2 pi over 2, we're going to get 6 pi over 12, which of course is going to simplify to pi over 2. So, now if this trend continues on throughout the entire circle, how will it continue? I want you to fill in the rest of these pi over 12 values. So they will continue on. We'll get 12 pi over 12, 14 pi over 12, 15 pi over 12, and on around the circle. Alright, so the next method that I want to show you is actually the one that I recommend using, because instead of having to think of our angle measurements as like 12s, we can actually just memorize half the circle here and then get the other half very intuitively whenever we need to. So it's called the mirror method, and it kind of goes like this. We have our unit circle, and we're going to fill in with memorization our top 2 quadrants, the radian angles. When we want to find, say, the measure or the radian value at this angle, what we're going to do is we're going to look at the opposite radian measurement, and we're going to add pi to it. And this is by definition of a circle what we're actually doing when we travel around it. So half of a circle is pi. That's the definition of pi. So that means going from this half of the circle all the way around to that half is going to be pi over 6 plus pi, which becomes pi over 6 plus 6 pi over 6, which becomes 7 pi over 6. And we can actually confirm this because we have a filled unit circle. We see the opposite side of pi over 6 is going to be 7 pi over 6. All right, so let's try another one. Let's do 2 pi over 3 here. So we see the opposite measurement is 2 pi over 3, so we're going to add pi to 2 pi over 3. So 2 pi over 3 plus pi is going to be 2 pi over 3 plus 3 pi over 3, which is going to equal 5 pi over 3. And again, we go up to our unit circle, and we see that, yep, this measurement right across from 2 pi over 3 is in fact 5 pi over 3. A way to shortcut having to get a common denominator here is to simply, when we have 2 pi over 3, so instead of getting a common denominator, what we can do to shortcut that is to just add the denominator to the numerator and then keep the denominator. So we're going to say 2 plus 3 pi over 3, and that's going to equal 5 pi over 3, just like we did right here. It's going to give us the same answer. And similarly for pi over 6, if instead we did pi over 6, where we add the denominator to the numerator, we're going to get 1 plus 6 pi over 6, which is going to equal 7 pi over 6, exactly what we got. So I now want you to fill out the rest of the circle using this method and without peeking back at our original unit circle. So now we can talk about the function values of sine and cosine. You may have noticed that there are actually really only 5 values on the unit circle, and those values are either positive or negative. So these values are 0, 1/2, square root 2 over 2, and square root 3 over 2. Sorry, that's a typo. And 1. This makes it much easier to memorize as well. So let's look at a single quadrant. We have quadrant 1 here, and we have our labeled unit circle. If we look at these triangles and account for their meaning, we see that this long but short triangle is going to have a length of root 3 over 2 and a height of 1/2. This middle triangle is going to have a height of root 2 over 2 and a length of root 2 over 2. And then finally, our pi over 3 triangle is going to have a width of 1/2, but a height of root 3 over 2. Now, these values are kind of unknowns, right? Root 3 and root 2, they're just going to be like, 1.4, 1.7, roughly. But these triangles should show us that 1/2 is going to be less than root 2 over 2, and that's going to be less than root 3 over 2. So, right, here's 3 over 2, here's root 3 over 2, here's root 2 over 2, and then here's 1/2. And then similarly, here's 3 over 2, here's root 2 over 2, and here's 1/2. All right, so what's very nice about the unit circle is that this pattern of 1/2, 3/2, root 2, and root 3 over 2, 1/2 is actually going to continue on over the entire unit circle. it's just going to be either flipped or with different signs. So let's see how these values change for other quadrants. So here we have another unit circle, and I've filled in just quadrant 1. And I want you to imagine that we flip this first quadrant onto the second. What's going to happen is these values, this value is going to overlap over here. It's going to become 1/2 root 3 over 2. This value is going to come here to make this root 2 over 2, root 2 over 2. And then this value is going to flip all the way over here to become root 3 over 2, 1/2. Now, these are almost correct. The only problem that we now have is that we're in quadrant 2, right? But we have positive x coordinates. And all we do to remedy that is just to make our x coordinates negative. Now, we can flip our quadrant 2 values onto quadrant 3 to fill in those values. So let's do that now. We're going to flip that one here, flip that one there, and flip that one here. So here we got root 3 over 2. I'll make it negative to keep it consistent. Here we got negative root 2 over 2, root 2 over 2. And then here we have negative 1/2 root 3 over 2. And again, we only have to account for the quadrant. So in quadrant 3, x and y should both be negative. All right, so now we've filled in 3 out of 4 of our quadrants. And finally, we're just going to flip quadrant 3 onto quadrant 4. So here we have negative root 3 over 2, negative 1/2. Here we're going to have negative root 2 over 2, negative root 2 over 2. And here we're going to have negative 1/2, negative root 3 over 2. But again, we have to account for the fact that in quadrant 4, we should have positive x values and negative y values. So let's just positive up our x values. And there we go. We have the full table here that we can check by going back to our unit circle, right? So here we have 1/2 root 3 over 2. This becomes negative 1/2 root 3 over 2, which becomes negative 1/2 negative root 3 over 2, which becomes 1/2 negative 3 root 3 over 2. Similarly here, you can follow the same trend. So this makes it very, very easy to memorize our actual sine and cosine values at these points. If we just remember a single one of them, a single quadrant, we can fill in all the rest of them. Now, I want you to fill out a unit circle with the x and y values without worrying about the radians. Begin by copying the values for quadrant 1 and then using these past ideas and your own intuition about positive and negative values to label them. Then, fill out a unit circle with all radian measures and their corresponding x and y values. Try not to peek back at our original unit circle. Try to fill it out only with the ideas that we've gone over. Our final activity is to take 2 minutes to quickly write in words how you feel sine and cosine relate to the unit circle, and how the unit circle can help us define values for sine and cosine of some angle theta.